because of all you are here. Okay. Waiting line situation is trade-off decision. More service, service cost, increasing capacity cost against the inherent cost of waiting. So waiting line increase, decrease, and so on. Queuing system or waiting line system consists of three parts. First one is customer arrival, source of population, and then system itself, and then exiting system. First part, customer arrival part, source of population or arrivals, finite or infinite. Finite population, limited size of customer, infinite population, no limit or large enough size. You know, Scranton, the population is, I heard about 70,000. What do you think? 70,000 population, is it finite or infinite?
Finite.
Finite?
Yeah.
Okay. Half right, half wrong. Depending on the service system capacity. If a serving system capacity is like one customer per day, then to handle all 70,000 days need. So that case, 70,000 is not large enough. That case, 70,000 is infinite population. But like a computer system, in a second, 70,000 like a name or information process. That case, 70,000 is finite, small enough. So finite or infinite, depending on serving system. And then distribution of arrival rate, the number of units per period. Like an hour, how many customers come to the store or facility. So the number of customers come to the system, that is arrival rate. And then two types, constant arrival or random arrival. Constant arrival, in certain time unit, like 1 hour, 10. Next 1 hour, 10. The same number of customers come to the system, the same number of arrival. That is constant arrival distribution. And then variable usually follow exponential or Poisson distribution, just random, not the same number, sometimes 10, sometimes 5, sometimes 6, different number of customers come to that store or facility system. And customer arrival in queue distribution, already we talked about, and the pattern, controllable, uncontrollable. Earlier we mentioned about the price difference. Earlier cheaper, and then later regular or expensive cost or price. Using different costs, yield management. Using yield management, if we can control customer size, then it is controllable pattern, but usually the pattern is uncontrollable, very natural. And then size of arrival, sometimes one by one customer, next one, but in a manufacturing system, usually batch by batch, 100 100, 200, 200, and so on. And then degree of patience. If you go a store and then grab some whatever you need, and then look at the waiting line long, then some people just wait and then buy, pay and then out. But some customers impatient, arrive, view, and then, oh, too long, just leave. Or look at that and then wait some time, but oh, I gotta go, then later move, leave, and so on. So impatient, patient. And system itself factors length of queue, infinite potential length, limited line capacity. But usually, potentially, the queue, the waiting line length is infinite. But limited line capacity, this case, traffic system. In street, intersection, and then light is red, and light is green here. Then cars, pass this intersection and then stop here because it is no red. Then if on this street or for this traffic system, this one is this light traffic system, and then this one for this space is for this one. But anyway, even this one is green. If it is red, then cars, this capacity is full, then usually cars stop here. So for this system, if the space is only 4 cars can stop, then this system's queue or waiting line is limited. But many people use this system as unlimited. Then this one changed, then car stuck here, and then traffic jam and so on like that. So basically, for this system, waiting line is limited. And the number of lines, waiting line, single waiting line and multiple waiting lines. You know, McDonald's and then Burger King use different queuing system. McDonald's, if there are 3 order station or cash station, whatever, if there are 3 the same, then McDonald's, if all 3 open, then make line for each. But Burger King make 1 line here, and then later distribute like this. So Burger King use only 1 waiting line, single line waiting system, and McDonald's use this system. You know, when I came to the United States about 30 years ago, In Korea, in restroom, use this system. So men's room or the ladies' room, make a line for each kind of. But when I came to the United States, Korea used this system, but in the United States, use this system. So I went to the first day of when I arrived in the United States, I went to Universal Studio in LA, California. Then I went to the restroom, then wow, using different waiting line system. I think it's better because like a privacy. And now Korea use this online waiting system in the restroom. So McDonald's and then Burger King use different types of the waiting line system. And next, queue discipline, first come, first serve. You know, whoever come first, then give a service first. And shortest processing time, you know, SOT rule, when we cover scheduling, shortest operation time or processing time. That is, if we can use this one, always shortest total time rule. And reservation first. You know, reservation, whoever has a reservation, when we reserve something, then we call and then using different words. Can I make a reservation or can I make appointment? Why we use different words? Can I make a reservation? Sometimes can I make an appointment? When we use appointment, when we use reservation. Did you think about it? Just yeah, because it's kind of natural. So you know when you use reservation, when you use appointment, but you didn't think about why is appointment, why is reservation. I will tell you. If you reserve time for see a doctor, then you call make an appointment, right? And then if you want me to see me, then appointment, right? But when you go somewhere and then airline ticket, nowadays we use computer, internet, reserve airline seat. But if you call an airline, then what do you say? Can I make a reservation, right? Or a hotel room, make a reservation. So if you reserve person or people, then appointment. If you reserve place, like a seat, room, or something facility, like you go picnic, then you need like a shelter, then you call somewhere and then make a reservation, right? So if you reserve people or person, appointment. If you reserve place, then reservation. Make sense? So anyway, reservation or appointment first, and emergency first, emergency room. One time, I drove to emergency room because of my son. When my son was like about 1.5 years old, I went to the emergency room. Before I went to the emergency room, I called, and then I need to go. I think it is emergency. Then the personnel asked me, blood or not blood. So, oh, now it's no blood, but then the personnel said, oh, it is not an emergency. If you can see blood, then whatever, I will go. And then I drove about 100 miles per hour speed on 35 mile street. Then a police car chased me. So stopped. Oh, it is an emergency. Then, oh, just go, just go. So whoever blood first. So emergency, then give the first service, and limited something like it's similar to reservation, like ticket holders give the service. And then service time distribution, constant and random. Constant, if like the car washing machine, then if you choose the same option every time, then the service time is the same, always the same. That is the service constant, the same service time, and then usually random service time, sometimes 10 minutes, sometimes 5 minutes, different times. And then line structure, single waiting line, like a McDonald's, single phase, like an ordering system. Then order, done. Then next one is eating. But this time, because of pandemic, now some restaurant open inside, dine in, but I don't go there. So just pick up or drive through order. So that case, single phase, and then order, dine in, multiple. The multi-channel, like a McDonald's, then single phase or a multiple phase, and mix it, multi to single channel. This case, like construction part, highway, 3 lanes, then here construction, then they go 1 lane here, so traffic jam here. So this case, multi to single channel. This time I live in Drums, about 45 minutes south from Scranton, our school. This time only one time I go Marriott for teaching in class. Then usually I leave from school around 8 o'clock. Then I think construction this time on 81 near Scranton area start at 7. So near the Scranton exit, 180, about 185, construction. So at night, 3 lanes plus 1 lane, so always traffic there this time. So that is now multi-2, single channel structure, and then alternative structure, you know, customization. Type A need 1 to 5, type B need 1 to 6, and so on. So different paths for each product or service. That is an alternative path. Okay, then next. The exit line, the last part of the queuing system, exit line structure, usually single channel, just to go out, and then a single phase out, and then done. And sometimes the customer come back for a reservice, but probably is low. Waiting line models, based on factors, we can use different models. Model 1, 2, 3, 4. Model 1, a kind of basic model, single channel, 1 waiting line, and a source of population, infinite or finite, and exponential pattern. That means service time is random, and then others the same. So based on this, single channel, multi-channel, if it is multi-channel, then we need model 3. If service pattern is constant, the same service time, then use model 2. And source of population, if it is finite, limited number of customer, then we use number 4, model number 4. Example number 1, customers in line. A drive-through window service. You know, usually drive-through is only one channel, only one waiting line. But recently, McDonald's used 2 waiting line, 2 drive-through order system, but usually only one. So we assume only one channel waiting line, and average arrival rate is 15 cars per hour. Average service time is 3 minutes. So if it is single channel and then source of population infinite and then exponential random service time, then we use model 1. Then using this model, waiting model, we can determine how many customers in waiting line, and then how long they wait, and then how long they wait, how many, and then in the system and so on. To get that kind of information, we need arrival rate and service rate. This notation, we can read this one as lambda. Arrival rate, lambda equals, is given 15, and service rate, because this example gives us service time, but service rate, mu, is how many. 3 minutes is not how many, how long. So 15, that is the time unit is hour. So convert this time, service time, to how many. So 60 minutes is an hour. So 60 minutes divided by 3 minutes. So 20 customers can be served. So service rate, arrival rate is how many. And then utilization. This notation we can read as raw. Raw equals lambda over mu, arrival rate divided by service rate equals 15 over 20.75. This means with this arrival rate and service rate, this facility, this system work 75%. Okay. And then using formula, we can get how many customers in waiting line. So when you go there, and then how many customers usually in drive-through. That is LQ, length of Q equals arrival rate squared divided by service rate times service rate minus arrival rate. So just plug in, then 2.25 cars for customers in waiting line on average. And then LS, total customers in the system, including waiting line and then being served. So lambda over mu minus lambda. So 15 divided by 20 minus 15 equals 3 cars, customers in the system. Okay, then how long wait in waiting line? That is, wait in queue equals LQ, how many customers in waiting line divided by arrival rate. That is 2.25 divided by 15 equals 0.15 hour. If we times 60, then in minute, 9 minutes wait in waiting line. And then average total time, including waiting time and then service time. LS, how many customers in the system divided by arrival rate. So 0.2 hour times 60 and 12 minutes. So total time is 12 minutes. And example 2, equipment selection. A robot washes a car at the rate of every 5 minutes. So robot washes. So this service time is constant. Every time the same. So if service pattern or service time is constant, then use model 2. Arrival rate is given 10 and service rate, if it uses 5 minutes for a service, then 60 divided by 5 equals 12. LQ, without 2, this one, the same as model 1, but constant model, model 2, here 2, and then 2.08333 customer in the waiting line, LS, LQ plus utilization, so 2.08333 plus 10 over 12 equals 2.91. And then WQ, how long wait in the queue? Use this one or this one, LQ divided by lambda. LQ is 1.08 divided by 10.20833 hour. And then total time, WQ plus 1 over service rate over LS time divided by lambda, arrival rate. So LS is 2. LS here, this one, 2.91666. So 2.91666 divided by 10 is 0.2910666 hour. And next one, example 3. Determining the number of servers. If multiple channel waiting line is multiple, then use model 3. So using this model 3, we can determine if now is single or multiple, doesn't matter. If hire one more channel, that means one more worker or one build up one more pay station. So currently 3 clerks work. That means the channel is 3. And then this store open 8 hours, service rate 20, customer arrival rate is 40. Then cost of a service clerk is $6. To hire one more clerk, $6. And then cost of customer waiting in line, $12. If customer wait in line an hour, then $12 worth. Then we can use a chart to find LQ. To use that chart to find the LQ, how many customers, we need utilization rate and then the number of servers. So raw utilization, lambda over mu, 40 divided by 20. So this one's utilization is 2. That means 200%. If only one channel, then this system work 200% of capacity. So using the chart, utilization is 2, and then the number of server is 3. So rho is 2, S equals 3. So from the chart, this chart is in lecture note. First column is utilization, and second column is the number of server, and then third column is LQ. So utilization is 2, the number of server is 3, then LQ, length of queue, how many customers in waiting line is 0.889. So if 3 servers work, then customer cost, LQ, length of queue, times customer cost, if customer wait in an hour in waiting line, then $12, and then the store open 8 hours. So if 3 servers work, then customer cost is $85.34. Then if hire one more, increase one more channel, S is 4, the same utilization, 4, and then LQ is 0.174. So if hire one more and then 4 workers work, 4 channels, then customer cost will be LQ 0.174, $12 customer cost per hour times 8 hour, this store open, then $16.70 customer cost. Value of customer's time saved. When 3 servers work, customer cost 85.34 minus when 4 servers work, customer cost is 16.7 equals 68.64. So by hiring one more clerk, increase one more channel, this store can save customer cost $68.64. But increase one more channel or hire one more clerk, pay $6 per hour during open, the store open 8 hours, $48. So finally, save this much, but pay this much. So save 68.64, pay 48. So final result is 20.64. So by hiring one more clerk, this store can save this much. So by this result, based on this result, if this result is positive, then hiring one more, increasing one more channel is worse because this one is positive. But this result is negative, then decision is don't hire or don't increase. Increasing, not worse. So using this model 3, we can determine if we hire one more or increase the channel by this result. And then using this model, we can get LQ already. If the 4 servers work, then LS, how many customers in the system. So LQ 0.173 plus utilization rate 2.173 customers in waiting line. And waiting time, WQ, LQ divided by arrival rate, LQ 0.1730 divided by 40, 0.0000004325 hour. That is about 15.57 seconds. So hiring one more, this one, very short waiting time. And then total time, WS, LS over lambda equals 2.1730 divided by 40 equals 0.054325 hour. That is about 3.2592 minutes. So not bad. And probably a waiting in line. When 4 servers work, then customer go there. Then if there is waiting line or not, the probably waiting in line PW equals LQ times the number of server and the utilization minus 1, so 0.1730, and then S is number of server 4, and then utilization 2 minus 1, that is 0.173. So chance is 17.3% when a customer go there, and then the chance of waiting is only 17%. And example number 4, finite population model. Like a traffic system, the only 4 cars can stop, then the waiting line is finite. If there are 5 laser printers in a system, like in a school, department, and so on, and then repair after about 20 hours, we use breakdowns and have been determined to be poison distributed. So arrival rate is random. The one technician on duty can serve a printer in an average of 2 hours. So 2 hours. And then following on exponential distribution. So service time is 2 hours, and then arrival time is every 20 hours about. Single channel, source of population finite, then use model 4. We need probably a system is empty. No one is in the system. Lambda is 0.05, 0.05. And then mu is 0.5. 2 hours, 20 hours. How can be lambda is 0.05? Arrival rate is 0.05. So an hour. So 1 hour is time unit. Then every 20 hours, customer come. So in an hour, 1 divided by 20. So 0.05. And then 2 hours. So every hour, 1/2. So arrival rate is 0.5. And then n, that is 5, the number of the customer. And then lower case n, that is 0 customer, 1 customer, 2 customer, 3 customer, up to 5. So using this formula, probability of 0 customer in the system 1 over sum of n equals 0 to 5. N is 5. So 0, 1, 2, 3, 4, 5. N is 5. Uppercase n is 5. Factorial. N 5 minus n from 0, 1, 2, 3, 4, 5. The lambda 0.05 divided by mu 0.5. This is utilization. N power. N is 0, 1, 2, 3, 4, 5. So if we use this formula, calculate this P0, then it will be P0 equals 1 over n is 5 factorial divided by, n is 5 minus 0 factorial times 0.05 divided by 0.5, 0 power, plus 1 over 5 factorial divided by 5 minus 1 factorial times 0.05 divided by 0.5 and 1 power plus and so on. So it's a very long calculation, but the answer is P0 is 0.564. I used Excel. I like Excel. So use Excel. They calculate that. Can you see? So I use the formula factorial. Oops. This part when is n is 0, 1, 2, 3, 4, 5. So this part, oops, this part, when n is 0, 1, 2, 3, 4, 5, that part is this one. So factorial n divided by factorial uppercase n minus lowercase n when it's 0, and then times utilization lambda over mu and n power, lowercase n power. So made like that, and then type in uppercase the number of customer 5, lambda 0.05, mu 0.5, and then or the numerator, and then add or numerators 1 over sum of those. So 0.564. So probability of system is empty, no one, nobody, customer in the system, that is 0.564, because to get LQ, we need a P0. So first we get a P0. The LQ is the number of customer minus arrival rate plus service rate divided by service rate times 1 minus P0. So 0.2 printers usually in waiting line in 1 hour. And then average number in the system LS, LQ plus 1 minus P0. 1 minus P0 means the probability of any customer in the system, because P0 is no one. So 1 minus P0 is any customer or work in the system. So LQ 0.2 plus 1 minus 0.564, that is 0.64 printers or customers in the system. And waiting line, how long? LQ divided by the number of customer minus LS, length of system, how many customers in the system, times lambda equals this 1.91 hours waiting line. And then total time, WQ, WS is WQ plus 1 over service rate, that is 2.91 hour. Wow. Whew. Kind of long, right? What do you think? Because other instructors don't cover this part, but I like, and then I like to let you know in case. So just briefly, very fast, just went over. There is no assignment from this chapter because this one is not a required part, but I just went over for your in case in the future. Even you don't know how to do it this time, but later, in case you need this one, then that is kind of waiting line situation. Then you can come back and then remind. Then you can find something reference. So just give you idea. That is waiting line, model, and situation. So that's all. And we have only one class on Thursday left. Okay. So even it is a short class tonight, but that's it. And if you don't have a question, then see you on Thursday.
Thank you. Have a good
Thank
night.
you.
Good night.
Good night.
Bye.